welcome to The Explainer. Today, we're exploring a pretty wild physical paradox. We're going to look at a material you've probably encountered at the dentist's office, or maybe you've seen it lining the walls of a hospital X-ray room. We're talking, of course, about lead. It's widely considered the absolute heavyweight champion of radiation shielding. But how exactly does it work? And honestly, more importantly, when does it utterly fail?
Okay, let's dive into this. Just think about it for a second. Radiation is a form of highly penetrating energy that can effortlessly slice right through thick concrete walls or even solid steel plates. Yet to protect our bodies and our environments from this invisible danger, we rely on a metal that is so incredibly soft you can literally scratch it with your fingernail. How does that make any sense? Well, to understand why, we first have to understand exactly what we're hiding from.
So the invisible threat we're dealing with is called ionizing radiation. This includes high-energy waves like X-rays and gamma rays, as well as fast-moving particles like beta particles and neutrons. And the danger here is right in the name, ionizing. These particles and waves carry so much energy that when they crash into living tissue, they can actually strip electrons right off your atoms. That scrambles your DNA and damages your cells. So to stop this from happening, we need a material that can catch or deflect this energy long before it reaches us. That brings us to Section 1, lead's atomic superpowers. To really understand this, we need to shrink down and look at lead as a microscopic fortress. Its very first superpower is its atomic number, 82. This means every single atom of lead has a massive nucleus surrounded by a highly dense cloud of 82 electrons. You can think of this electron cloud like a giant microscopic catcher's mitt. When ionizing radiation, like an X-ray, tries to pass through, it has to navigate this massive, crowded minefield of electrons. The sheer number of electrons just drastically increases the probability that the radiation is going to collide with one of them and be stopped dead in its tracks. The second superpower is extreme material density. Lead clocks in at an incredible 11.34 grams per cubic centimeter. So it's not just that each lead atom has a lot of electrons, it's that these atoms are packed together incredibly tightly. Because of this extreme compression, the physical distance that radiation can travel before it inevitably smashes into a particle is drastically shortened. And that's exactly why a relatively thin sheet of lead can do the same exact job as a much thicker wall of concrete. Moving on to Section 2, the physics of stopping power. So what actually happens at the exact moment of impact? The crucial point here is the photoelectric effect. This is lead's absolute best weapon, particularly against the lower energy X-rays you'd encounter in, say, a medical clinic. When an X-ray photon enters the lead shield, it strikes one of those 82 electrons. But it doesn't just bounce off. It transfers 100% of its energy to the electron. The photon literally vanishes. It's completely absorbed, and the radiation threat is instantly neutralized. And this brilliantly illustrates why lead completely dominates. If we look at the probability of different interactions based on photon energy, you'll notice how high atomic number materials, like lead, massively outperform lighter elements when it comes to just swallowing that incoming radiation whole. Basically, the heavier the atom, the more efficiently it absorbs that energy. But what if the radiation has a bit more punch? Well, lead handles that with something called Compton scattering, where the photon hits an electron, transfers some of its energy, and then violently ricochets away much weaker. And for extremely high-energy gamma rays, lead facilitates pair production. This is where the photon's energy literally converts into physical matter. It's wild. But in every single scenario, lead's massive structure forces the radiation to exhaust its energy. Let's look at Section 3, the practical material hero. Let's zoom back out to the real world, where engineers are actually building hospitals and labs. Why is lead the unrivaled king of construction? Ultimately, it comes down to density versus economics. Tungsten is actually much denser and stronger than lead, but tungsten is roughly $50 a kilogram, and it's incredibly difficult to machine. Lead, on the other hand, is abundant, costs a fraction of that at around $2.50 a kilo, and is remarkably soft. And you know that softness, its incredible malleability, is its real practical superpower. You can melt it, mold it, and shape it into almost anything without it ever cracking. You can stack it as interlocking bricks for a temporary nuclear barrier. You can roll it into paper-thin sheets and glue it right to the back of standard drywall for a dentist's office. You can even spin it into wearable aprons and blankets. There is simply no other heavy metal that offers this level of highly customizable, affordable protection. But that brings us to Section 4, Lead's unexpected kryptonite.
Because here is the major plot twist of our explainer. Lead is absolutely not a universal shield. First up, neutrons. Remember how lead relies on its massive cloud of electrons to catch radiation? Well, neutrons have no electrical charge. They are completely neutral. Fast-moving neutrons will ghost right past lead's electron cloud as if it's not even there. To stop neutrons, you actually need a complex three-step obstacle course. First, you have to slow them down by crashing them into light hydrogen-rich materials like water or plastic. Then, you absorb them using something like boron. Finally, because absorbing a neutron often triggers a gamma ray, you then put a layer of lead at the very end just to catch that secondary gamma ray. But lead all by itself? Completely helpless here.
But it gets even wilder than just being helpless. Because sometimes, wrapping a radioactive source in a thick layer of lead will actually make the radiation hazard significantly worse. This mind-bending phenomenon is known as Bremsstrahlung, which is German for breaking radiation. When you have high-energy beta particles, which are essentially just high-speed electrons, and you try to block them with a high atomic number material like lead, the beta particles violently decelerate. That sudden, violent braking action converts the particle's kinetic energy into brand new, highly penetrating X-rays. So you've essentially built an X-ray machine by accident. You stopped the beta particle, sure, but you just created a much more dangerous secondary emission in the process. Let's move to see how this builds a totally counterintuitive safety protocol. If you're working with a strong beta emitter, like phosphorus-32 in a lab, you absolutely do not reach for the lead brick. Instead, your primary shield needs to be a low atomic weight material, like clear plastic. The plastic gently decelerates the beta particles without generating those massive secondary X-rays. Only after the plastic does its job do you wrap the outside in a thin layer of lead, and that's just to catch any minor, low-energy Bremsstrahlung that might have squeaked through. And of course, stepping back from the physics for a moment, we can't ignore the real-world biology. Despite its unrivaled ability to stop X-rays, lead is highly toxic to humans and the environment. Handling it requires super careful protocols, and disposing of it as radioactive waste is a massive, highly regulated challenge. The European Union and other regulatory bodies are constantly pushing industries to find eco-friendly alternatives like bismuth or polymer composites, simply because of these severe contamination risks. Which leaves us with a really fascinating dilemma. We are highly dependent on a material that is functionally brilliant, incredibly cheap, yet environmentally hazardous, and sometimes totally ineffective against certain atomic threats. Lead's unique balance of atomic density, high electron count, and low cost makes it a really tough champion to beat. But as medical and nuclear technologies advance, and as environmental regulations tighten, the search for the next great atomic shield is absolutely on. So what do you think? Will innovation eventually render lead completely obsolete? Or will this ancient heavy metal always be our ultimate line of defense? Definitely something to think about. Thanks for exploring this explainer with me.